Okay, I'm continuing to work on this Victor 706B Geiger counter, and it was time to lift one leg of that capacitor and check it, and boy did I blow it. I thought it was a zero point 0.4 microfarad. It's not, it's an electrolytic. I couldn't see it because it was facing the board, so I undid one, checked it, and got a ridiculously high um, um, reading on it, and I'm like, what? That don't make no sense. And then I noticed two colors, yellow and red. I'm like, oh, it's an electrolytic. So I turned it around, and it's 400 microfarad at 3 volts. So I got it discharged, but it's not a very high voltage, 3 volts, right? It's got no voltage, it's just on the battery supply. So if we check the capacitance on it, which of course it's bad because it is an electrolytic. And get on my capacitance test there and hook my alligator clip back to the probe, and you'll see it'll read. Right now that's saying nanofarad, you can see it there. Now it's on millifarad, so 711 or 710 millifarads. It's actually leaking DC, that's why it's dropping. So it's roughly 700. It's supposed to be 400. You talk about way out. That is way out. So just for kicks, I wanted to compare my little cheapy digital meter there. Oh, it's back up to 700 with this Chinese meter that I use to do semiconductors, and it's kind of cool looking thing. It works. And if I go on here with this and test it, back up a little bit here, and it says 659.7 microfarads. So it's pretty close, right? That one's saying 700, this one's saying 660. So there's a tolerance there. I would imagine this is not as accurate as my digital. But that's okay because this thing is designed to test all kinds of controls, so it's got a higher tolerance. But then it checks with a different voltage source. So yeah, that's got to go. That is a big problem, and I did not catch it. So I'm going to take it out. Now I don't think I have a 470, which is what we would use. It's not critical, but I don't have any 470s at 3 volts, but the voltage don't matter as long as it's higher than what it needs to be. So let me go see what I got, and we'll do a comparison. Okay, what I found is a 470 at 16 volts, so it's well within tolerance. It's reading 461. So 400 plus or minus 80%, well, 410% would be 40, so 20%, plus or minus 20%. 10% of 400 would be 40, so 20% would be 80, and this is 461. It sure is a whole lot closer than that 700 that's in there. That's supposed to be 400. But the bigger issue with electrolytic capacitors is not so much the value. That's why, they don't make these. They make these. You almost can't even get axial capacitors anymore, with a lead on each side. Instead, you get these aerial capacitors because they're made for printed circuit boards where you just stand them up, right? So anyway, this one's 3 times the voltage, so we don't have to worry about any voltage spikes hurting it because it's really strong. It's a Nichicon. I only use Nichicon and what's the other one? I only use the expensive capacitors. I don't use cheapy capacitors. I get my capacitors from Mauser.com. I know they're not Chinese knockoffs, and they're good capacitors. So that one will maintain that voltage, which will stay within the tolerance. And again, this is just the control for the switching. What did they call it? They called it an integration capacitor. And on the schematic, it's just this guy here, which maintains enough voltage for the meter, which, It just maintains a voltage across the meter, basically. And it's controlled by this resistor, so you even got more tolerance there to zero out the meter. That's all that's for, is to zero out the meter. So we're going to go ahead and use this one and take this one out. What I started to say is the reason that these capacitors got to go is not so much that they are, way out of tolerance. It's that they leak direct current. They're not supposed to act like a resistor. And you see how stable this one is. It's jumping around in the third digit point. And see, it's just staying there in that range. It'd go up and down a little with my batteries and the meter, but you see it's staying right at 460. Okay, if I put this on here, and let it get to its ridiculously high level, 692, 697. See how that third significant digit changes. And of course now it's on the millifarad scale instead of the microfarad scale. So we don't even know what's happening in the fourth position. All we can tell is by it changing. Okay, getting ready to calibrate this. I got the new capacitor in. You can see it right in there. I'm shine a light in there for a second. See him standing up there? He's soldered in and everything's good. Got my meter here, digital meter on milliamps on the battery supply line. And what we're going to check is the high voltage, or what we're going to calibrate. There's two ways to do the calibration on the high voltage. First off, if you don't hear that buzz that I was talking about yesterday in the last video, you know the high voltage is not working. Well, it is working. We are currently on. We can check it two ways, and this is the way we're going to do it. The other way would be to check the high voltage with a probe, but we're going to just check the current draw and make sure that we get the right current draw. And so we need to set the high voltage potentiometer or calibration control so that we turn it all the way on fully clockwise, full high voltage, and then we back it off, and we advance the screwdriver counterclockwise, so we back it off until we get 33 milliamps with new batteries. Well, these are new batteries. So if I turn it all the way up, and use an insulated screwdriver, obviously, because this is high voltage, turn it all the way up. Okay, that's all the way up. We're at 12 milliamps. We need to be at 33, so we back it down until we get to 33 milliamps. And I'm going to check it a couple times, but okay, right, it's a little sensitive. Right about there. That's pretty good. So there's 33 milliamps of current going through the oscillator. And the meter should be moving when I move this probe over here. And it is. It's moving fine. Yep, it's moving fine. Okay. See, maybe I can get a better angle. See the indicator bar moving in there, the coil? Oh, sorry, right there. See it? So it is registering, it is oscillating, and it is right around 33 milliamps. Okay, when it's closed, it'll only do gamma rays. When it's open, it'll do the sample. It'll do beta rays, because that's beta there. And you put it on 10, you should get, I mean right now I'm getting normal ground noise, ground radiation. Should get around 0.2, or well 2 because it's times 10 MR per hour. What you do is you got to put the dot there in one of these. Actually, the center one's the best, and it needs to be in between the metal plate so you get an accurate reading. So if we put that directly there, I'm trying to stay out of the way of the camera. I don't think I'm doing a good job of that. Let me move it over here. You just have to take my word for it. When we put it there, you see we're way up. So, well, of course, it's got to kind of set to itself, but it's coming down a little. All right, so that should be 2. So what we got to do is change the calibration on it. And that's on the side here where we did the high voltage calibration. So I'm going to turn that down some, just to kind of get closer to a ballpark. Okay, that's all the way counterclockwise, and we'll see what that does. Okay, so you see that took it all the way down. All right, so I'm just going to turn this calibration one like a little bit at a time. Let me see what that brings it. Okay, look at that. It should be between 1.5 and 2.5. So we should average about 2, and you see we're right about there. Yeah. So that's the peak. And that's a little bit high, but it's okay. We'll turn it back just a smidgen. Try that. Quite sensitive. Wow, that's really sensitive. I may have to just turn this sideways to do this. Get my power lead out of the way. Oh, we disconnected the power. Okay. I had that back there so it wouldn't tip over. Let's use that. Okay, well, let's see. I'm going to try to hold this here and do the calibration at the same time, which you shouldn't do at high voltage things, but get it at peak. Okay, that's peak there. Well, that ain't bad. That's about right. That's really good. So that's how you calibrate it. And so now it's accurate. And the high voltage side we did by setting the current flow from the batteries to 33 milliamps, and we're still there, if you can see that. And so we got that set because that's the best way to check the high voltage. So I'm going to move the camera a little bit and we will take another look at the document. Okay, I was able to find a better document on servicing this, and of course it gives you a little bit more information, but basically it said the same thing that I was saying, that you really don't need to actually measure the high voltage. You can if you have a high voltage probe. I don't have one. I don't work on TV sets, tube television sets and things from that era. so I don't deal with really high voltage. It's only 900 volts. Unfortunately, most of my meters do not go up to 900, and it's 900 plus or minus 20%, so it can actually be, well over 1,000 volts or over 1,000 volts, and I don't have a meter that goes that high. See right here, you turn the high voltage adjustment R5B fully clockwise, and then you turn the range switch to X times 100, and you rotate the screwdriver adjustment counterclockwise until the meter reads 33 milliamps. Now, the original document didn't say to set it to X100, it just said turn it on. So I went ahead and redid it, following this procedure, turning it fully clockwise, turn the range switch to X100, and then I reset it back to 33 milliamps. Before I did that, I turned it on a X100, and sure enough, it was still at 33 milliamps from the previous time. But I went ahead, shut it off, discharged the capacitors, set it to a fully clockwise, put it on X100, turned it on, and backed it back down to 33. So it really don't seem to matter, but I wanted to follow the procedure that the company recommended, and this is directly from them. So yeah, this is their documentation, and it's a little bit more in depth. See, the Victorian Instrument Company. It's more in depth than the other one that I had, this one here. So apparently this is an older document. They both say 1962, but this was probably more one that was distributed with the unit, and this one is more of a technical service documentation. It actually goes into more detail. It has some troubleshooting charts here. If I switch the view, you see it has some troubleshooting charts that the other one didn't have. Tells you where to check voltages and things like that. But we don't have a problem, so it's working. So we really didn't need this. There is, some test points they show here. This is where you check the high voltage on H. Everything's is referenced to this point, which is ground, which is, you see where the transformer rivet is there, and the other side of the transformer that we already looked at in the previous video. So yeah, this is reference to ground. You check the voltages. It also shows what I was showing in the previous video, where these battery wires connect. Because when they originally made this, they didn't use stranded battery wires. They're solid, and anytime you move a circuit board around quite a bit, like we've been doing, a solid wire can just break, right? Because you're bending it back and forth or moving it around, it can just break solid copper wire. But since the new battery boxes have stranded wire, that's less of an issue. But just to know for sure, in case the wires popped off while we were working on it, I did that short little section of the last video where I actually documented where all the wires connected. That's a good habit to do, because when you're working on something like this, sometimes you don't have a schematic. And then if a wire breaks, you can spend a good hour trying to figure out where that wire went to get it right. So it's always good to make a video document of where the wires go. I do that all the time working on tube radios and tube guitar amps and things like that. I'll take a video of where the wires connect before I disconnect wire harnesses and things like that, even on hi-fi stereos. So yeah, it's a good thing to do. But that's what they're doing here. They're showing you the same kind of scenario, so you would understand what's going on. And on this one too, let me switch back to the other view. They also show you where the test points are here on the schematic diagram, which I thought was really neat. So you can see where all of the test points are. I didn't go through and do all of them. I did do some. I did this one. I did this one. Check the voltage here when we did the calibration. Before I did the calibration, I checked the voltages, and sure enough, they're what they're supposed to be. I didn't check anything on the high voltage side, of course, They're saying reference to here, which is basically ground, right? It's the same side here. It's the ground of these two batteries. So yeah, so everything's working fine, and I'm ready to wrap this up. What I'm going to do is paint the inside of the case, permanently mount the battery boxes in there. Now that we're done moving it around and checking test points on the circuit board, checking components, I'm going to go ahead and take the old wires from the old battery box off and solder the new battery boxes directly to the circuits as they go here in the schematic diagram, you know, here. So as it is here, I'm just going to connect them like that, the way they're supposed to go, and put it back together, and then work on painting the case. I already fixed the jack on the headphone, and the headphone works. So I got that back soldered back on, and it works. It's you know, it's not as nice of a sound system as I would have thought it would be, but it was 1962, you know. So you hear the clicks, and that's basically all you need to know is it's clicking. You can use this without the headphones, because it's the meter that really tells you how much radiation you're getting. So the next thing I will show you is once the batteries are permanently matched to the unit, then we'll look at that, and we'll look at the case, and I'll get the schematic. After I paint the inside of the case, I'll get the schematic attached in there, and it's done. So anyway, I hope you found this video series, this two-part series, interesting, and we will continue it and finish it with this process, and it'll be completed, and hopefully that'll be beneficial for you. Thank you for watching. Okay, I got this guided counter box painted. It's not a perfect match, but it's good enough. At least it'll help keep that corrosion from getting worse. Get the schematic diagram glued down in there. There was a lot of corrosion in this box, places where it almost went through. I gave it a couple coats of paint and primer, so it should be fine. Now to reassemble it all. Well, here's the battery boxes reinstalled on the unit, and it looks good. So I'm going to go ahead and put the batteries in it. We'll put it back in the case and do a check. Alrighty, here it is, back in its case. So we're going to do a test. Put this on times 10. The needle moved a little. Set this near the... There we go. So yeah, it's doing its job. And it'll fluctuate between 1.5 and 2.5 or so. There it goes. So it's warming up, you know. But yeah, back together. There it is. And there's the probe. And let's see, we'll check out the headphones too. Give me a second. Okay, there's the headphones connected to it. And let's see if you can hear that. Hear that? And we're right on 2. Apologize for the other noise. But yeah, there it is. It's back together, back in its case, and it's functioning fine. So it's ready to go back to its home. And it'll be actually put into service. They're actually going to use it where it's going. So that's good to hear. So anyway, I hope you found this series interesting on the repair of this Victor CDV 700 Geiger counter in 1962. Anyway, thanks for watching. If you've enjoyed the video, I'd appreciate it if you give me a thumbs up, and subscribe if you want to follow other videos that I'm working on, other projects that I'm working on. Actually, I got the next one on the bench that I already started on. This is a chassis out of a Tombstone radio. It's a 1935 Harvard Model 77, 7-tube with sideband. And we disassembled everything to the chassis so I could do some cleaning, but we're getting ready to recap it and restore it and get it working again. So if you find vintage and antique electronics interesting, please consider subscribing to my channel, and appreciate it, and hope you all have a great day. Thanks for watching.